So now we have learnt about the Poisson's equation. Once we have done that, we are in a position to discuss about solution of electrostatic fields within dielectrics, which means that if I have a dielectric on which an external applied field has been subjected, and to understand whether it is going to be able to withstand the electrostatic stresses within the insulation, I should be able to plot the electric field within the volume of the material. And to do that, what are the options or what are the techniques available to me? Firstly, as we have already mentioned, we can use Coulomb's law, we can use Gauss's law. However, to use either Coulomb's law or Gauss's law, we need to know the charge distribution. That means we need to know the location of the charges and the magnitudes of the charges that are located within the volume of the dielectric or in the neighboring region. And obviously, in practice, this is hardly true. We hardly ever know in reality what are the charges, what is the charge distribution in my power apparatus. And therefore, application of these techniques for determining electric fields in practical situations is almost an impossibility. So when I need to solve electrostatic fields in practical situations, I have to recognize that what I do know is at some of the boundaries, I am probably aware of the boundary conditions. And when I say boundary conditions, I mean I'm aware of the electrostatic conditions at the boundaries. That means I may, for example, know the potential at a boundary, or I may know the charge at a boundary. For example, if you take the case of a parallel plate capacitor, I would know the potential on the capacitor plates, on the top of the dielectric and the bottom edge of the dielectric. I know what the potential is. I may even know if there is any free charge present on the sides of the capacitor. But I would know the charge density, but I would really not know what is the location of the charge points on the capacitor plates. So essentially, I have to recognize that plotting the field in a dielectric reduces to a boundary value problem, that is a solution of a boundary value problem subject to certain boundary conditions. And this is where the Laplace's equation or the Poisson's equation comes into the picture. Because if I solve Laplace's equation or Poisson's equation, I am solving a boundary value problem. Now, if I solve Laplace's equation for a particular in a particular solution regime or in a particular region, subject to certain boundary conditions, can I be sure that this is the solution that I'm looking for? This is the electrostatic field that I'm looking for. I'll obtain a solution in terms of potential distribution. And once I have potential distribution, I can calculate the electric field distribution as the gradient of the potential. But is this the solution that I'm looking for? And this answer comes from what is called the uniqueness theorem. If a solution to Laplace equation can be found such that it satisfies certain boundary conditions, then the solution is unique. That means you can find only one unique solution which will satisfy the given boundary conditions for that particular region. This is also true for Poisson's equation. So that means what I need to do is to obtain the electrostatic field in a dielectric medium, I need to solve the Laplace's or Poisson's equation, depending on which is applicable. A boundary value problem is uniquely defined by the appropriate differential equation. So if you have volume charge density, then you have to solve Poisson's equation. If there is no volume charges within the volume of the dielectric, and here volume charge means free charge density, then it means then you have to solve Laplace's equation. One thing we need to remember is that when I apply an external electric field across a dielectric, what I have is the Laplacian field, which can be obtained by solving for del square phi is equal to 0. Del square phi equal to 0, subject to the applied boundary conditions, is the field within the dielectric because of the external applied field. Over and above this, if I also have volume charge density, that means there is a source of charge within the dielectric, and each charge within a dielectric will exert its own electrostatic field. So the situation in the presence of volume charge density is that there is on the dielectric an external applied field, and superimposed on that external applied field is a Poisson field which is a field which comes because of the charge distribution within the material. So even if you did not apply any potential difference, you would have some field because of the Poisson field, and if you did not have any volume charge density, you would still have the Laplacian field. So Poisson's equation gives me a solution for electrostatic fields, which is a superposition of these two separate fields. So I have to choose the appropriate differential equation. Whether I have to choose the Laplaces or Poissons depends upon the presence or absence of volume charge density. I have to figure out which is the solution region in which I want to plot my electrostatic field or potential, and to obtain a unique solution, I also need the prescribed boundary conditions. Now, when I talk about the Laplace's equation or the Poisson's equation, this is a second order partial differential equation. Any second order partial, a general second order partial differential equation is represented by this equation. So you have several terms, d2 del 2v del x square, del 2v del y square, del square v del x del y. So this is, of course, if you consider a two-dimensional region. If you have a three-dimensional region, then you will also have the del square v del z square terms. So in two dimensions, this is your partial differential equation. Now, this is the general form. Some of these coefficients a, b, c may be 0. As we know, this is my Laplace's equation, del square v del x square plus del square v del y square is equal to 0 in two dimensions, which means from this equation, a is equal to 1, b is equal to 0, c is equal to 1, again d is equal to 0, e is equal to 0, f is equal to 0, and g has a certain non-zero value if it is the Poisson's equation, equal to 0 if it is the Laplace's equation. Now, if these coefficients satisfy the condition that b square is less than ac, which it does in case of Laplace's equation, then such a partial differential equation is considered to be elliptic. You can have elliptic PDE, you can have hyperbolic PDE, you can have parabolic PDE. We are not going to discuss that, but Laplace's equation or Poisson's equation is an elliptical second order partial differential equation. Why is this important? Because generally elliptical equations have boundary conditions which are specified around a closed boundary, which means that if you have a region in space where you want to compute the electrostatic field, you can only do that by solving Laplace's or Poisson's equation, provided you know the boundary conditions on all the boundaries. So the boundary, it's a closed boundary, and on every boundary, the boundary condition has to be specified. It can be specified charge, free charge, or it can be specified potential, or when I say charge, it means I can specify the flux density, the change in flux density across a boundary. So dn1 minus dn2 equal to rho, that would be specification of charge, or v equal to v naught, v equal to 0 would be the specification of potential. So on all the available boundaries, either of these boundary conditions have to be specified, then and only then will it be possible for us to solve Laplace's or Poisson's equation to obtain the electrostatic field map within the region.